So today we leave the box, we leave the particle in a box. We'll start with that a little bit, but then we'll branch out and we'll actually show some real molecules. How about that? All right, so we'll jump in. We had this sort of culmination of the particle in a box. This was the simulated stick spectrum of an electron in a box. And you spent all week doing calculus. And so your calculus results gave us these selection rules. The odd numbered transitions are allowed according to analytical calculus and the wave functions and these integrals that we did. And symmetry provides an easier path to these selection rules. So, how many, when you did this by hand, did it go past one page, this problem? Anybody? You got a nod here. Yeah, so, and if you write small, I mean, maybe you can fit it on a page, but still, it goes on and on and on, especially all the substitutions and then the integration by parts and everything like that. And if you know the symmetries of the wave functions, really, you can determine if that transition is allowed on a Post-it note. And so you can just look at the symmetries, and we'll learn how to do that today. So let's look at our wave functions. You'll see today why I really wanted that box to be centered on 0. Okay, because if we have our wave functions that are centered on the origin, then we can look at the left and right sides of these wave functions to see if they're symmetric. Okay, so if we look to the left, we just go an arbitrary distance to the left. So x, so we're going this function of minus x, and compare that to the value of that function at positive x. We can see that they have the same value. Okay, so we have this, and this is the definition of an even function. So if we look at the left side, the negative x part, and the right side, the positive x part, and they're the same. In this case, you could think of it as a mirror image, but it's actually an inversion. But anyway, we can look at it. It's nice. You could put a mirror down the middle, and you would see the same thing on both sides. Now, what do I mean by mirror? Well, if you ever, I don't know if you've ever seen this. We used to have, I was in gymnastics, and we had this mirror so that you could see your how you were posing or positioning your body, if your legs were straight, if your toes were pointed, and so on. And so we had this mirror, but it was a movable mirror, and it was on wheels. And you could stand on the mirror and put the mirror down the side, and you could pick up this leg, and it looked like both legs were up. Okay, and so we would do that and have a really funny time. So when I say put a mirror down the middle, I mean put a mirror here so that you're looking at the right side, and then you see the reflection of the right side in that mirror. And then the wave function looks the same, the one we've highlighted right now. Okay. If I put a mirror on this one, it doesn't look right. The thing is below here, it's below here, but over here, in actuality, it's above. And so we would have to take the left side of that and multiply by -1 to get it to work. And so that's the definition of an odd function. If we go to the left an arbitrary distance and we go the same distance to the right, it's the same shape, but -1. And so that -1 in front is what makes it an odd function. So the left and right sides are opposite of each other in sign. Okay, same shape, but different sign. So it's really important that you be able to look at a function and recognize whether it's even or odd. Now, for a single dimensional function, I'm making it sound really difficult. It's not. Look at the left and right side. If one's positive, the other's negative at the same spots on the curve, that's an odd function. If they're both positive here, like you've got a positive region here and a positive region here, the same distance from the origin, that's an even function. Okay. When we're dealing with a p orbital, we might have a p orbital here like this around the atom, and the top is shaded. Guess what? The top is shaded. The same distance down is not shaded. That's an odd function. Okay, but it's in 3 dimensions. But it's the same kind of concept. You go from the origin out and see what the sign is. You go the opposite direction, see what the sign is. If they're opposite sign, it's an odd function. What about an even function? Let's take that dz squared orbital. And it's got that little ring around the middle that's shaded. Okay, you recognize that as a dz squared orbital? I go away from the origin and I pick a point here, and I go through the origin and pick this point the same distance on the other side. They're the same sign, so that's an even function. So this one's even, this one's odd. Okay, and these things in front of those functions, when you do this operation, are called characters. And in symmetry, when we get into the symmetry elements and group theory, we're going to have tables of characters. So there's going to be character tables that we deal with. And the character table has all of the symmetry of all the different motions and electron cloud and everything associated with that molecule will be captured in that character table. We only have one dimension here. We only have one type of function, so we only have one, character. It's either even or odd under inversion. So let's look at our selection rules. We had these various transition probabilities, and now we can see what the symmetry of these integrals are. And so the definitions of even and odd functions, one of the definitions, is that the integral over all space of an even function is non-zero. That's huge. So we can put a star by that one. Okay. And the integral of an odd function is 0. Big star. And that makes sense. Let's just draw that ground state function. If you notice, if I integrated this over all space, it's positive everywhere. And my integral result would be non-zero. If I integrated an odd function over all space, I have a positive piece, but I also have a negative piece. And so that integral would be 0. The positive pieces and the negative pieces would cancel out when I add them all up. Now that's over all space. If I integrate the first half, then that's not the integral over all space. So. And then we can know how these functions, when you multiply one by the other, you have these multiplication rules. And so if you have some function that's even and a different function that's even, and you multiply those together, you're going to get an even function in the end. Okay. In fact, we can just make a shorthand. Even times even equals even. Even times odd equals odd. Odd times odd equals even. Now, these words even are, if you look at these multiplication rules, they're the same multiplication rules as the plus ones and minus ones. So when we're thinking of even functions, really be thinking like plus 1 and minus 1. We're not talking about being divisible by 2. So when we're dealing with even functions and odd functions, we're looking at the positive and negative regions in terms of their phase around the origin. We're not talking about divisible by 2. So in symmetry, even means something different than it does just in arithmetic. So minus 1 times minus 1, that's the same as odd times odd, and that's going to be a plus 1, right? And in fact, if you have an odd number of odd functions, it's also going to be odd, right? Because you have 2 of them multiplied by each other, that makes an even function, and then you have the even result times the odd, and you're going to get an odd result. And so the integral over all space, if you have an odd number of odd functions, then you're going to have an integral of 0. And you'll see that over and over and over again. So let's do our symmetry selection rules for the fundamental transition. So is the intensity of the 1 to 2 transition allowed by symmetry? So here's our transition dipole moment integral squared. And what we want to do is we want to know, without getting into all the analytical calculus, whether this integral is going to be 0 or non-zero. We can't really tell what it will be, but we can tell if it's 0 or non-zero. So that'll be nice. It'll save us some time. And so we're going to substitute that in. If we look over here, the n equals 1 wave function is even, and so that goes right here. The n equals 2 is odd, so that goes right here. And then the x-axis, if I were to plot the x-axis on the x-axis, right? So here's the origin, 0, the x-axis, and if I go over to, so f of x equals x, right? So that's that function right there. So if I go over to, x equals 2, then I plot a 2. And if I go over to x equals minus 2, my plots in minus 2. So that's the x-axis, if I were to plot that. And is that an even function or an odd function? And I just said, if I go over to 2, it's positive 2. If I go to negative 2, it's negative 2. And so that's going to be an odd function. So the x-axis, which represents light, is an odd function. So I know now the symmetry of all three functions inside my integral. And I can use my even and odd multiplication rules to simplify things. So I take these two, odd times odd gives me even. And then I do this multiplication rule, even times even gives me even. So I know that the overall integrand inside my integral is going to be an even function. And by definition, the integral over all space of an even function is non-zero. So I know that this is going to be an allowed transition. And so we say this is allowed by symmetry. I haven't done the analytical calculus, but I've done the symmetry analysis, and so this would be allowed by symmetry. Do you need any clarification on that? Okay. So let's look at some other ones. Okay. So let's do this one here, the 1 to 3. So we have n equals 1, that's even. Can I just use e's now? And then x is odd, and 3 is even. Okay. We just put these vertical lines here just to show there's three different functions there, but we can combine these two. Odd times even is odd. And then even times odd is odd. So this is going to be the integral over all space of an odd function, which is equal to 0. So that's forbidden. And that's 4 lines. If you had this particular transition in the lab, the 1 to 3 transition, it took you several lines of calculus and, burning a lot of brain cells, okay, to get through it. And here I know that my answer is going to be 0. I could still show the math, but my answer is going to be 0. So at least I know where it's going to go, okay? And then the 1 to 4 transition, so we look at 4, that's odd, x is odd, 1 is even. And so you'll see that, we just follow the same thing. Odd times even is odd. And I bring that one down. Let me go do my little lines like that. And then odd times odd is even. So the integral over all space of an even function is not equal to 0. And so that's allowed by symmetry. Yeah, let's try that. Okay, so it's just been the way with operators. You sort of work from right to left, but you will get the same answer either way. But this is the way. So this lecture, if you come back and do this, get in the habit of doing it from right to left, but you will get the same answer. Because if you do, let me just do it over here to the side, odd times even. These first two become even. Okay, so odd times odd is even, and then you have even times even. So you get the same answer. In these particular problems, you get the same answer. Okay. Symmetry operations are not necessarily commutative. And so it matters the order, but in none of our problems in this course does the order matter. But this is just the traditional way to do it. Yes.
So in the middle, how come x is how do we get that x is odd?
Okay, so thinking about I was trying to show that here. So if I've got a plot of this function, and my function is some general function f of x, right? So it's sort of y, right? Y is equal to x. That's that function. So f of x plotted versus x. If that f of x is just x, right? Like you could have a coefficient in front of it, but there isn't one. Okay. So 1 times x plus 0, right? The linear equation. So whatever X value I have, that's also the Y value. So it's just a diagonal line. Yeah. And if I look at that, you see that if I go to the right, I have positive values. If I go to the left, I have negative values. And that's the definition of an odd function.
Okay, so it's always odd?
It is always odd.
Okay.
Yeah. Now, when we get to scattering, we're going to use x squared. So let's plot x squared. So here's 0 in the middle, and we'll plot this f of x and x squared. So if I go, 0 squared is 0, but then all the other x's are positive. So this is x squared. Plotted on the x-axis. And so if I go to the right a certain distance, it's a positive number. If I go to the left that same distance, it's the same positive number. And so this is going to be even. X squared is an even function. And that will change the selection rules for Raman, and they'll be different than the selection rules for direct absorption and emission. So that's great. I'm glad you asked that question because I hadn't done the x squared on here, so I wanted to do that. So those things in the middle are going to determine our selection rules. We have the wave functions, and then what the light, however light's interacting. If it's just a single photon, which would be x, or if it's 2 photons, it's scattering, it would be x squared, then we'll have different selection rules. So this is a real-world evidence that symmetry matters. Here's water and CO2. Both have 3 atoms. Both have different numbers of vibrations in the infrared spectrum, and this is the single beam infrared spectrum. So if I just look at a hot source through air, this is what I'm going to see. So this is kind of a black body radiation curve. Can you kind of see that? It looks backwards from what we're used to seeing, but it's like a black body radiation curve. It's got a maximum that would shift based on temperature and so on. So this is the infrared light coming off a hot object. And then these lines are going down because there's light missing. So wherever there's water or CO2, it absorbs some of that light, and so it's missing. That's why you have the lines going down. So this is what we call a single beam spectrum. I'm just looking at a hot object, and I see some missing light where there are rotational lines for CO2 and water. So here I've labeled the CO2 vibrations, and I've labeled the water vibrations. And I've zoomed in. Look how pretty this is. I have a single peak in the middle, and then very regular bumps. These are rotational lines. And later we'll realize that this is the J equals 1 to 2 or 2 to 3 or 3 to 4 transition. So these are the rotational lines. And look how just organized, I should say. I say pretty because it's pretty to me, but what do I mean by that? It's very organized. It's a very clean pattern. But look at water. That's a mess. Okay? And the symmetry of CO2 restricts the selection rules. And so we have a very clean spectrum. Water's bent. And so it's not as symmetric as CO2, and it has a very dirty spectrum. There's peaks everywhere. The selection rules are relaxed, and you have lots of allowed transitions. Whereas if you have a very symmetric molecule, a lot of those transitions are forbidden. And so they don't show up. Even if light comes in and has the correct energy, the symmetry won't let that molecule absorb that light. And so this is proof that water is bent and CO2 is linear. You can just look at this spectrum and know, even though they both have 3 atoms, they have very different symmetries. And so that's pretty cool. Here's more example of this automobile exhaust. We've got water here and here, but let's focus on CO2. There's a symmetric stretch of CO2 where if my head is the carbon and my hands are the oxygens, this is the symmetric stretch, okay? But this is the asymmetric stretch. That's my favorite dance move. Okay, and then and so that one is infrared active because there's a dipole that swaps back and forth as it's moving. But the symmetric stretch, no dipole, so it can't interact with light. So that's because it's symmetric. That is pushed to the Raman spectrum and doesn't show up in the infrared. So here's another example that this Raman active only, that tells us that CO2 is a linear molecule. If it was not symmetric, then that peak would show up in the infrared. So all of the peaks in water show up in both the infrared and the Raman, but in CO2, we have this rule of mutual exclusion. Any molecule that has an inversion center, and we'll learn what that is later on, has IR vibrations that are active and Raman vibrations that are active. And CO2 falls into that category. So we know because of this that CO2 has to be linear. So let's talk about symmetry. It seems to not just work for the particle in a box, it also works for 3D molecules like CO2 and water. And it's very easy. We just did the symmetry analysis of the selection rules with the one-dimensional system. So particle in a box, super easy. Particle on a ring is, if you'll notice on, I forget which chapters in the book, I think it's 7 and 8, that the particle on a ring is much more difficult than the particle in a box, but I think it's still easy. The hydrogen atom radial wave function is lowercase easy. But when you get to molecules, the wave functions are impossible. So doing this by symmetry really helps. We can learn molecular orbital theory very easily for diatomics. We get to polyatomic molecules, 3 atoms or more, and it gets much more difficult. And symmetry helps us understand symmetric molecules, and local symmetry helps us understand parts of molecules that are symmetric. So think of a methyl group. A methyl group has threefold symmetry, right? I can rotate it 1/3 of a turn and you see it kind of snap hydrogen to hydrogen. Now that methyl group can be stuck on, say, DNA, really a really big molecule or some enzyme that's crazy big. The methyl group will still have threefold symmetry. So that's what we mean by local symmetry. We can understand some of the behaviors of molecules even on a local level, even though they're attached to larger molecules or attached to a surface. So let's look at symmetry. This is the main point of the course. This course is quantum mechanics and spectroscopy. Now, quantum mechanics is where we get the wave functions. And the wave functions are what you're looking at when you're looking at orbitals, p orbitals, s orbitals, and so on. And also when you're looking at molecular orbitals. And so how do we understand those functions? We're going to use symmetry to understand those functions. And so this slide, notice I put the point. This slide is going to be the point for the rest of the course. So we're learning this, week 2. We're sort of lining out the rest of the course, and we're going to go through this material 4 or 5 times with different spectra, visible spectra or infrared or Raman and so on. So direct product tables tell us how to determine selection rules for spectroscopy. And where do we get those direct product tables? Well, we get those, and they are parts of character tables, or they help us understand how the character tables interact. And character tables allow us to understand the symmetries of the molecular motions, the symmetries of the molecular orbitals, the interactions of equivalent nuclei, say in infrared or in NMR. And then we get the character tables from the point group of the molecule. And notice I put this character table up here. Do you know what this thing is over on the right? Rosetta Stone, yeah. So we did not know how to interpret hieroglyphics. When we discovered all of the, Egyptian temples and pyramids and so on, we go in and there's pictures everywhere. What does that mean? We had no idea, but we knew Greek, okay? And when we found the Rosetta Stone, we had Greek down here, Demotic script here, and hieroglyphic script here, and they said the same things. And so whenever we're looking at the wave functions and the motions of the molecule, how we understand how those interact, that to you right now is like hieroglyphics, where it's the archaeologists, okay? And so you understand this stuff. Point groups, geometry of the molecule, Lewis dot and Vesper hybridization theory. And so if you can understand hybridization theory and Lewis dot structures, that's your ancient Greek piece that you learned a few semesters ago. And the character tables allow us to turn that into spectroscopy information. Okay, so that's fantastic. So the spectrum and the wave function is the hieroglyphics that you don't know yet, but you know about Lewis dot structures, and Vesper shapes. And if you don't, need to review those things. Okay, so review your Gen Chem. If you sold your book, okay, not only shame on you, but we can recover. This is a book called OpenStax. It's an open educational resource, and you can go through here. It's a Gen Chem book, and it's searchable, so you can come in, and so you have a freshman book here that can reteach you the Lewis dot structures and Vesper shapes and all of those things. Okay, so you start with the Lewis dot structure, and we use those electron domains to determine the 3D structure. So valence shell, electron pair, repulsion theory. Remember Vesper theory? And then we use that 3D structure to determine the point group for that molecule. And it's going to take us a couple of lectures to do. So this is what I call, the freshman molecule on the left, where everything's 90 degrees, and then you've got to transform that over into this Vesper shape. And my little drawing program doesn't do all the little dashes here, so those are dashed. Now, notice how I've drawn this molecule. This course requires careful drawing. I'm not necessarily, your TA on the Symmetry Lab will grade your drawings, okay? So you will be graded on your artwork, at least once, right? But I really want to emphasize this mainly because you won't see the symmetry unless you draw it well. If I do the freshman molecule and I say, okay, one of these is a wedge, and one of these is a dash, but I'm going to leave these at 90 degrees, then I'm really hurt myself because I can't see that this hydrogen is right in front of that one. Whereas over here, I need to show these hydrogens very close together so that I can see, if I put a mirror in the plane of the paper, that I can see that that hydrogen will reflect right into that hydrogen and vice versa. So if I reflect those through the mirror, if I draw them close to each other, I see that one's in front of the other. And so when I do a reflection operation in the plane of the paper, then I see that the one reflects into the other. Over here, I can't see that. So don't draw your molecules like this. Okay. Draw them like this. Do your best to show that this is 109.5 degrees and that these are right on top of each other so that you can see the symmetry. And then you can also see that this is a threefold axis. So it has, this is what we call a C3 axis. If I rotate that 1/3 of a turn, this hydrogen comes down into this one, this hydrogen goes back into that one, and the back hydrogen comes up to the plane of the paper. And so I see that threefold symmetry. Over here, I can't see any rotational symmetry because I've drawn everything in the plane. And just because I add wedges and dashes doesn't really change the visual picture of it. So once again, I'm going to put 2 marks through it. It doesn't allow you to see reflections or rotations, and so it's just not a good way to draw your molecules. And the same thing with these different hybridizations. So how do I know that's a 109.5 degree angle? That's because that's an sp3 carbon. And this one here is an sp2. How do I know that? It has 3 electron domains. 3 domains require 3 hybrid orbitals, an s and 2 p's. We always start with the s. And so I've got 3 domains, 3 hybrid orbitals. The s counts as 1. We don't ever put a 1 up there, but you see how this is 3 hybrid orbitals. And this one is 4. An S and 3 P's for the 4 electron domains. So that's a little review of the freshman Vesper theory, valence shell, electron pair, repulsion theory. Let's go through those words. Valence shell, we're only looking at the valence electrons. Electron pairs, each bond involves some combination of pairs of electrons. Repulsion, they hate each other, and so they're going to try to get as far away as possible. And so these are the 3-dimensional shapes that allow those electron domains to get as far away as possible. And double bonds and single bonds, this acts as a single domain of electron density. So, okay, so what is symmetry? Symmetry is defined by the number and types of symmetry operations that leave the object unchanged. So like my mug here, it has rotational symmetry because I can rotate it any degree and it leaves the shape unchanged. If I were rotated a different axis, it would appear to be changed. Let me say that again. But if I rotate it along this axis, it doesn't change its shape. And so it has a rotational axis this way, but not a rotational axis this way or that way. What about a sphere? Well, a sphere has an infinite number of rotational axes. I can rotate it around any axis and it appears unchanged. I've shown some shapes over here that are spinning. This is an octahedron and a tetrahedron, two very common shapes in chemistry. And they actually have point groups of TD for tetrahedron and OH for octahedron. Get to know those, okay? So they're very common shapes. So the sphere is the most symmetric object because it has an infinite number of planes that you can reflect the object through. It has an infinite number of rotation axes. It has an inversion center, and so it has the most. So the sphere is the most symmetric object. Why do we care? Well, think about this cube and these two rectangular prisms. You know, if I label each face, say A, B, and C, and I keep track of the energy of that object based on which face it's sitting on, notice that the center of mass is what gravity is acting on. So I can calculate its potential energy and sort of plot that according to each face. And what I would have would be energy on the y-axis, and the energy on face A, B, C, and so on would all be the same. So I would have 6 equal energy levels. One being the energy of A, the next one B, the next one C, D, E, and F. And notice how the more symmetric the object, the more degenerate energy levels I have. What about this object here? If I labeled the big flat faces A and then B, and then these ends, let's label the next largest size C, and on the back D, and the ends E and F. Notice how if I'm on the big faces, my center of mass is the lowest it could be. Okay, and so in this particular object, I would have A and B here. If I put them on the next largest faces, they would be higher in energy, but still C and D would be degenerate. And then if I put them on their small ends, E and F would be even higher energy, E and F, but they would be degenerate. So you see how the symmetry affects the energy level diagram. And we're not even dealing with wave functions. We're just talking about macroscopic objects. So, group theory helps us understand how the energy level diagram behaves based upon the symmetry or shape of the object. Same thing can happen with wave functions. So here are the symmetry elements that we will deal with. These are point group symmetry elements. There's also space group elements, which deal with crystal structures, which we're not going to get into. It's way too much for this one semester course. This is plenty. But these 5 symmetry elements will be possessed by the molecule if you can operate on the molecule and it appears unchanged. And we'll practice here in a sec. So there's identity, there's a rotation axis, there's a mirror plane, an inversion center, and then rotation, reflection axis, which is also called improper rotation. You still see it in the literature, so I want you to know that term, but I guess it fell out of favor because it sounds like a moral claim. It's an improper rotation. Don't do that. When there's nothing moral about it, it's just a rotation and a reflection in the one operation. So we'll look at all of these. The commutative law is not necessarily obeyed, and we can show that in a minute. So this is just talking about each of the symmetry operations. I'm going to leave that in your notes, not read this to you. Let's go learn by doing. So let's go to this symotter.org website. Okay, and I'm going to try to figure out how to get this browser to show up. Let's see. Okay, that'll work. Let's see. Yeah, that's going to be fine. Okay, so we have the SymOtter website, and there's a bunch of different options here. We have the symmetry tutorial, the gallery, and the challenge. Let's go to, let's go to the tutorial. So here are the different symmetry elements. Notice there's only 4. There were 5 on our earlier list, but the identity is just multiplying everything by 1. So you don't have any motion at all for the molecule. So every molecule, no matter how strange and asymmetric, has the identity. So then let's look at the reflection operation. So this is pretty cool. Here's ammonia. You can move it around. So go have fun with this. If I were to draw this molecule, oops, let me reset that. I hit the middle button. I don't know. Okay, here we are back. They've got kind of a cut plane going here. Let me reload the website. Okay. Yeah, okay. So this is ammonia, and it has a rotation axis. So if we here it is down here. So if I select that, you can see all of them. Let me just look at one. Okay, so you see that mirror plane there? And the nice thing about this is you can animate it. So this is what we mean by having a reflection. You see, so it's reflecting the whole molecule through that plane. Now the nitrogen in the middle is also being reflected, but it's just one half of the nitrogen reflecting into the other half of the nitrogen. So when the atoms are in the plane, you don't really see much happening. Let's look at this one. Okay, and then that just connects those 2 hydrogens to each other. And then this one connects these 2 hydrogens to each other. So if I animate that. So does everybody understand the reflection operation? You notice all these symmetry elements will go through the center of mass of the molecule. So you draw, if you were to draw this on a page, notice how close those hydrogens need to be drawn so that you can see that they reflect into each other. Okay. We can look at it from the top and animate it. So, okay. Let's look at inversion. So this is a molecule, a square planar molecule. I guess we could come up with a better one, but let's do ethane, staggered. Yeah. Okay, this is staggered ethane. You see how it looks? Okay. And let's look at the inversion. So this is maybe how I would draw it on the board. I would have a wedge here and a dash going in the back, and a wedge here and a dash going in the back. Notice the 2 planar hydrogens are opposite of each other. So that's how you would draw a staggered ethane. And it has an inversion center, which is the center of mass of the molecule. And let's animate it. Every atom goes through the center of mass to the other side. Okay. And so that's the inversion operation. Okay. This one has a lot, so let's just look at their rotations now. Let's look at the C3 rotations. Okay. And so that threefold symmetry axis goes through the center of the molecule and goes down the carbon-carbon bond, and so we can rotate it. So that's rotating 1/3 of a turn. So if it's a C3, it's 1/3 of a turn. What's a C2? 1/2 of a turn, 180 degrees. C4, 1/4 of a turn. Now it shows that it has 2 rotations. So how do we keep track of our rotations? Well, you pick a hydrogen and you see where it goes. And so let's pick that one on the right, and it rotates towards us and goes to the hydrogen outside of the plane. Well, the C3 minus one goes the opposite direction. So it takes that same hydrogen and moves it to the one on the back. Okay. So we have two unique C3 operations, sort of clockwise and anticlockwise. We also have three C2 rotations. So can you see the C2 axis coming out of the plane of the paper? So the hydrogen in the plane of the paper could rotate and stay in the plane and go around to the other hydrogen. Let's pick the one I'm talking about. No, it's this one right here. So you see that C2 axis, and I'm going to rotate the molecule. So that's 180 degrees, 1/2 of a turn, and now the molecule appears unchanged. How do we know it appears unchanged? Do an experiment with me. Look at the molecule. Now everybody close your eyes. Close your eyes. Close them, close them, close them. Okay. Now open your eyes. Did I do anything?
Yes.
How do you know?
I heard the mouse click.
Okay, very good. Yeah, but other than that, you can't tell. And that's what we mean by the symmetry element, right? If you reflect it and you get the molecule back, then it's like an eigenfunction. You operate on it, you get it back. Okay, so that's what we mean by possessing a symmetry element or a symmetry operation. Okay, if I change this hydrogen to a chlorine, then I don't have staggered ethane anymore. I don't have this point group. It changes the symmetry elements. If I change all the hydrogens to chlorine, I get it back. I have the, all of the same rotations and reflections and everything. But if I break symmetry by changing this atom to a different type of atom, then it's no longer a hydrogen and it won't rotate into a hydrogen. If there was a chlorine here and you closed your eyes and I rotated it, you'd see it up front. And you'd say, oh, I see that you did something. Okay, then it doesn't have that symmetry element. If you can tell the molecule's changed, it doesn't have the symmetry element. Okay. Let's look at methane. Oh no, let's go back to, let's do this one. Let's do the improper rotation of the rotation reflection. Okay, this one's very cool. So this has a rotation and a reflection plane, the S operations. And so it's an S6. So I'm going 1/6 of a turn. I rotate 1/6 of a turn and reflect. So 1/6 of a turn and then reflect. 1/6 of a turn and then reflect. Okay. So that's the rotation reflection operator or improper rotation. And that sort of captures the symmetry across the middle of the molecule. We have a reflection, a rotation, and a reflection. Now think about how if you were to put labels on your hydrogens, all of these symmetry elements do is just change the labels, right? They're still hydrogens, but label 1 went from hydrogen 1 over to some other hydrogen, and label 2 went from hydrogen 2 over to some other hydrogen. And the carbons also change labels. So carbon 1 up here is now down here. Okay. And then we have different kinds of reflections. So if you turn all of these on, you see all of the symmetry of the molecule, and it's kind of ridiculous. But you can see that's a very symmetric molecule. We can do the same thing with methane. We can turn on all of these. So it's got lots of reflections, lots of rotation axes. See, here's a C3 axis. It's got some rotation reflection planes and so on. Okay. So these are all of the symmetry elements that we have to deal with. There's only 4 of them plus identity. So it's not that bad. What we will do eventually is get to this point group business where we have to figure out what the point groups are. And if we go back, let's see, how do we get back? Here we go, symmetry challenge. There's actually a flow chart that you can go through to figure out what the point group is. And so you've got this molecule. It asks you questions whether you can see the symmetry elements. And so you're looking at this molecule and you say, does it have an infinite rotation axis? No. That would be a C infinity. It would be a linear molecule. Does this molecule contain 2 or more unique C3 axes? Does it have any C3 axes? I see some C2s, but I don't see any C3s. No. So then you go through all these questions and you'll eventually arrive at the point group for the molecule. Why is that important? Once you know the point group, then you have the character table, and then you know the symmetries of all of the properties of the molecule. Right. So I think that's enough for us now. Okay. There's a Kahoot on here, but you don't know the point groups yet, so wait on the Kahoot. You can try it next week. So y'all have a great weekend.